Hey everyone, so we're going to do a few problems here. Does anyone have problems in the chat? We're going to work some chapter 15, I think. Just name the problem you want me to work. I've got them open in the background right now. I've got my Word document, so I'm ready to take notes. I've got a bunch of chapter 15 problems here ready to go. So name the problem you want. We'll start working right here. The quiz, which one on the quiz? Which one on the quiz shall we start working? And thank you for everyone who puts all these timestamps in. I know a bunch of people have been watching the videos, doing the timestamps. And remember, we work through the problems, we do all the steps, and then we make sure how to interpret it. 1950s, let's find that one. 1950s. So we need to find the 1950s one. In the 1950s, here we go. Now with this one right here, this is all about nulls and alternative hypotheses. So we have to know our steps to writing a null and alternative in statistical notation. Every time we write a null and alternative hypothesis, we always start by writing our null and just our alternative. So we start with just this right here. That just says the null says and the alternative says. Now there's going to be 3 spots for the null and 3 spots for the alternative. We have spot 1, spot 2, and spot 3. Spot 1, spot 2, and spot 3. Now what goes into these spots is very important. We have right in here in the first spot, we'll label this spot number 1. So this is all spot number 1, spot number 2, and spot number 3. So what goes into spot number 1 is what we are testing. Yeah, I can do some more here, Ashton, if you want. We've done sporadically differently throughout, but ask a question here and we'll do it next, Ashton. So the null is always equal. Amazing job right there, Sydney. We know the null has the equal sign. So we know the null, we'll do that in another color right here. We'll do it in, we're going to add a green pen right here. Let's go to pen. Let's add in a green pen for the answers. And so we've got the null has the equal sign. So the null has to have the equal sign. Now, the alternative can have less than, greater than, or not equal to. Now, you won't write all of these right here, but the sign is in the second position. So we have to know that the sign goes here, and we'll choose one of these. Like, we could be testing to see if something is equal to something or not equal, and then we would choose this. So the question might read, has it changed? That would be, we're just testing to see if it's not equal to. So we need to know what the alternative is. The question could ask, has it increased? So then we'd say it has increased, it's greater than. But what are we talking about here? That's part number 1. Part number 1 can be a few different values. It can be p in our class, it can be mu, or it can be mu1 minus mu2. I'm running out of room on this right here. But these are all the different things. We'll erase part 2 for a moment. But these are all the different things that can be in part 1. P, and that's capital P, mu, or mu1 minus mu2, and those are subscripts. So you'll see in a later chapter when we're comparing two means, the first thing we'll write here is that mu1 minus mu2, and then we'll put the equal because the null always has the equal sign. This is when you're comparing two means, like the GPA of UT versus Florida students. We could always do one mean and say mu equals to something. That's just saying like the GPA of students is equal to this. And then we could also do the last one here, which I think we're doing in this problem, is P, and that's the true proportion. So always try to read it as a sentence. This would say the true proportion of something is equal to some hypothesized value. And what you'll notice here is that we always put this like P naught. That means a hypothesized proportion. And so this is where this question's going, but let's talk about part 3 for a second, which is the hypothesized value. So we're focusing in on the third part right here, which is the hypothesized value. In this class, it'll be 3 separate things, either P naught, mu naught. Now you think it'd be mu naught 1 minus mu naught 2 or something like that, but the last one is usually 0. It doesn't have to be, but we're hypothesizing what the true difference between two means might be. So this is kind of analogous to over here on this side. If you're doing over here in the first part, if you're doing P, it'd be P naught. If you're doing mu, it'd be mu naught. And if you're doing mu1 minus mu2, you hypothesize that that difference is 0. Just to make it clear, these go in the following sections. This is part 1 section right here, and this is part 3 section. Part 2 is very easy, it's just the equal sign, but part 1 is either the true proportion we're testing, the true mean. Oh my gosh, someone's got to call me out. I've been writing little knots on things and nope, go away. That is not a knot right there. P, mu, or mu1 minus mu2. And then on the other side we have P naught, good to see you Carson, we have P naught, Q naught, P naught, mu naught, or 0. And P means the true proportion, P naught means the hypothesized true proportion. Mu means the true mean, mu naught means the hypothesized true mean. Mu1 minus mu2 means the true difference between two means, and then we're hypothesizing that that difference is 0. So you'll notice as we do these questions right here, we're going to follow these steps and make sure that we know where to put what. Now the whole reason we focus in on writing the null is because if we write the null that P is equal to 0.60, Well, then part 3 does not change and part 1 does not change. The only thing we need to focus in on is the sign now. We might be asking if the true proportion is greater than, less than, or not equal to the hypothesized amount. So if you practice writing the null, you can get the alternative down. So let's see how this applies to this question right here. Remember, focus in on writing the null correctly, and then we can write the alternative. In the 1950s, only about 40% of high school students graduated college, so this is what we are hypothesizing is true. So that'll go, whoops. So, oh, it already has it there. I thought there was a third part. So we're testing the proportion of people who graduate high school, and that's going to be P. It can only be P or mu from these choices. It's not a true mean. We're asking if people graduated high school. That's a categorical question. And the null always has the equal sign. Has this percentage changed? I need to see in the chat, since we're asking has it changed, what is the sign? What sign will we use? Greater than, less than, or not equals to? And Sydney, nice work in the chat. 1,000,000 points right there. We're going to use not equals to, and then once again, we're going to use P. Please note how this is P, and this is P, and this is the same. This is exactly what we're practicing right here, right now. Julio, nice work. 1,000,000 points, Julio. 20% of cars of a certain model have needed costly transmission repair. So it's whether or not your car needs repair. Does my car need repair, yes or no? That's categorical, making it P. We know the null always has the equal sign. The manufacturer hopes that a redesign has solved this problem. So if a car needs repairs and they're trying to fix this problem, we would hope that the amount of cars or the proportion of cars that need repairs would go what? Go up, go down, or change. If they're trying to fix this problem, we would hope that the proportion of cars that need repairs would go up, go down, or change. What sounds better? That the proportion would be less than it is right now if they fix it, greater than it is right now if they fix it. They want to show evidence that it'll be what? If they're trying to fix this problem. Go down, you got it, nice work. So that's where we read in the question, they're trying to solve it. And basically we're asking, is there evidence that it has gotten better? So that's very important right there. We test a new soft drink, planning to market it if only over 60. So this is very clear what the alternative is. They're looking for evidence. The alternative is the evidence-based claim. So they're looking for greater than 60. We know the null has the equal sign. And they're asking if people like a soft drink. That is P. So it's the true proportion of people who like a soft drink is equal to 60%. And the true proportion of people who like a soft drink is greater than. And we got that 100. Was there, Ashton, do you have a question on a specific problem? Feel free to ask it. Sydney, feel free to ask another one. Let's keep working some problems here. We reviewed nulls and alternatives in like 5 minutes right there. Can you help with chapter 14 quiz? Yeah, Katie, feel free. You're the next question on here. How do we determine when to use not equal? Yeah, so good question right here, Yuting. Then we'll do Katie's question. Ask a specific one, Katie. Be like, can you work this problem? And I'll work that problem for you right now. So, or let me go to the next one. The not equals is when it doesn't, well, one, it says like, has it changed? But if this were to say, you know, let's test the claim that 40% of people graduate from college, then we could use not equals. Like the question could just read, is it true that 40% of people graduate from college? Well, it's either true or not true then. We never use sample mean. Correct. Great answer, Julio. We'll never use p hat or y bar, because what are we testing right here? We're testing the true proportion, and we're testing to see if the true mean is equal to these things. So we always do a test on the truth right there. 1,000,000 points, all those answers. Can we do the governor question? Yeah, we'll do the governor one, then Katie, when she puts her question in here, is this the governor one? Tell me if I see the governor one, because sometimes they'll change what the person's called or something. Let's see if we can find the governor one. Tell me if you see it. Philanthropic organization. I don't see the governor one yet. If you can copy part of the start of the problem. It's the country club question. Yes, we'll do that one next here. We got that. That is next one we're going to do. We might do it now because I don't know if I see the governor one. I think it might be this very first one because sometimes they'll change the name of what the person's called. Is it this one, Sydney? Yeah, I think it's this one. They'll change. And look at this. Do you see how it's not highlighting that? That means it'll change it. So it's prime minister in this one, governor in the other one. And then we're going to do Katie's problem next right here. After the political ad campaign, pollsters checked the prime minister's positive. Yeah, they test the hypothesis that the ads produced no change against the alternatives, that the positives are now above. Okay, so no change would mean that they're currently equal to this. And is this it right here? Am I doing the full question? We can do the criminal jury one next. Well, we got Katie's question, then we'll do that one, Tracy. So are above 40% with a p-value of this. Now, what this would show is, let's show what this looks like graphically. So when we did this test right here, we have to think about how to draw it. So if we got a p-value of 0.425, I think it was, we would have landed somewhere about right here. We landed very close to the center. And this is the p-value. So this p-value here, I think, was 0.425. So what does this p-value tell us? It tells us the probability of observing this sample proportion. So we would observe a sample proportion at that red line, which is what they found in their sample. They observed maybe 41% or something like that. It was very close to 40%. But we would observe a sample proportion as extreme or more extreme, hence the shaded area, than whatever we observed 42.5% of the time due to random chance, given 0.40 is the truth. Now, I should do that in a different color not to cause confusion. What we're hypothesizing right now is right here. So at the very center of this curve is 40%, because we're hypothesizing that 40% is true. So tell me, do you think what we observed in this p hat right here was very likely given the null is true? Does it sound like a result like that or more extreme is very likely? We're going to do chapter 14 next. You got it right there. So we're going to hop to chapter 14, then we'll hop back to chapter 15. Do you think that this p hat was very likely? The likelihood of it is this area under the curve right here. And does that look likely or not likely? The answer is that's very likely. So we would not reject the null, all that good stuff. Yes, very, very likely. Nice job, Sydney. And so we go back to here and we look at this. This is the probability of observing a result as extreme or more extreme than what we observed, given 40% is true. And that's got it right there. Is that the one you wanted right there? It's a very short one, but it's an interpretation of a p-value to say the probability of our results or results more extreme happening by random chance variation, given that the null is true. Once again, we should look at the graphic for it and realize that when we talk about our results, that's what we observed in a sample, or results more extreme due to random chance variation, given the null is true. Awesome. Great job, Sydney. So remember, everything I'm highlighting here is what I'm saying. The probability of me observing a p-hat as extreme or more extreme due to random chance variation, given the null hypothesis is true, is this right here. So this is the probability of our results or results more extreme happening by random chance variation, given that null is true. Once again, I'm going to say it one more time, then we're going to do chapter 14. The probability of us observing this sample proportion of whatever it was, we don't know, in our sample, given 40% is the truth, it would occur about 42.5% of the time due to random chance variation, which is the normal curve showing what would happen due to random chance given the null is true. Really great questions right there. I think we've got a bunch of chapter 14. Name that question from chapter 14 that you want me to do, and we will hop over and do some chapter 14. Who has a chapter 14? Country Club, we saw that one. So let me pull up Country Club. I was thinking in the background. Chapter 14, I'm assuming this is confidence intervals. So let me go to confidence interval 1. And here we are. I didn't preview it. If I don't preview it, I don't get all the questions. Let's go here to replace questions. That's what I want to do. And here we go. And let's bring up the chat. Question 2 with hot dogs. Oh, we'll do the hot dog one first here because we found it, and then we'll do Country Club next. Wait, no, Katie's been here a while. Katie was here first, so we'll do Country Clubs, and then we'll do hot dogs. We know where hot dogs are at. So we should find Country Club question. Country Clubs. Where's Country Clubs at? You got it. And is it in the homework or the quiz? Here it is right here. I think I found it. It's the golf one with Country Club. There we go. So it's Country Club. Okay. So here's what we have to practice every time. Every time we do these questions, we have to write the notation. So we're going to take this right here and take all of our notation down. So let's practice doing our notation. We're going to take a little snip right here of, whoops. Let's go ahead and grab this. And let's go ahead and write all of our notation down we know for this problem so far. So always practice your notation. And here we go. The count is going to be one notation. I need you guys to help me out. Pause the video if you're doing this and try to write your notation. Really good practice. What is the count in notation? That's the easy one. So what is the count in notation? Does anyone know in the chat? Where in the Pearson site can we practice the group of them? The group of them, as in which group of them? I do not know. How many words a minute can you speak? A lot. A lot. I can type Sometimes I can type like 90 a lot of times. Sometimes I can type 100. Practice problems, I've seen them before. Yeah, you'll have to, if you find where that button's at, I think there's a way to do it. I think there's a way. Inform me if you see how to do it. There's like the quiz myself sections on my Pearson, so I know there's a way to do it, I think. Who knows what the count is? In notation, what is the count? We need to know our notation. We got to practice. I always tell my students to put all the notation in the back of your notebook, and then when you do it, yep. If you find it, Tracy, send me a screenshot if you find it. I'll look for it too, because there's like the skill set things to practice. Oh, does no one know what count is? Oh no. Oh no. Katie, Sydney, Julia, or Julio. What am I saying? I'm so blind, Julio. I can't see the screen, even though I can like touch it. Like it's right there. No one knows what count is. Oh no. Oh no. Yes, Katie, nice job. That's N right there. That's what count is. I'll do the next few. Thank you so much, Katie, right there. 1,000,000 points. Don't know if you're in our class, but we got 1,000,000 points right there. And then we got the standard deviation right here is S. So a big thing people might make mistakes on this question is that they might think that the mean is mu, but this comes from a sample, and they might think that the standard deviation is sigma, but mu is for population and sigma is for population and capital N is for population. This is all from a sample, so we use sample statistics, not population parameters. Now the last thing we can find is the degrees of freedom. Since this is a one sample t, the degrees of freedom will be n minus 1. So we just need to do n minus 1 to get the degrees of freedom. So I should write df equals df, that's a d right there, equals n minus 1. So that looked like a 2. There we go, n minus 1. So we can figure out the degrees of freedom are, degrees of freedom equals 201. So there's 201 degrees of freedom. This is important because we're going to need it for our formula. Our formula is y bar plus or minus t with n minus 1 degrees of freedom. That's subscript. We put a star because we get to pick it. And then we do s over square root of n. So this right here is going to be our confidence interval formula. So let's go ahead and start plugging in the numbers down here below it. The numbers are going to be 2, 8, 6. I don't know what numbers are. 6. There we go. 0.7 plus or minus, and then the t we actually have to find. So this is where people often get stuck on these, because every time you do a t statistic, you need to go to a thing like a t-applet. Don't use t-tables. That's my personal opinion. But t-applets are nice and easy because you put in your degrees of freedom. Let's go that we're building a 95% confidence interval, which it's already there, but I'm going to show it this way. And I'm going to put this in the link in the chat so people can go straight to this site. Now, it will be showing what I'm showing, but please notice what you have to enter in. You have to tell it the degrees of freedom, which is what we found from n minus 1 for a one sample t interval or t-test. And then we can go back to that. You got it. Hey, it's Jay. We got you next. We're going to do some more chapter 15 after this. Or we're doing chapter 14 now, yes. And then we put in 95 to go right here. Put any question you want in the chat. We're going to do the hot dog question next, and then any question you want, Jay. So we have right here a t-score, which is 1.972. And we go back to here. And we enter in 1 point. Hey, good to see you, Connor. And then we put in S, which is 9.6 square root. There we go right there. For t-values, do we always want the... so that's the big thing. When we do the nonprofit one next, we got hot dogs and nonprofit. So let's go back and look at that applet again and see what's going on with it. With this applet right here, you can use the plus or minus t right here, the minus or plus, when you're making confidence intervals. So take a look at this right here, this graphic, and realize that a confidence interval is the middle area contained. This one is the one you'll use for a confidence interval, one of the best ways to do right here. And then this one right here is the does not equals test. So usually you enter in your t-score right here. So when you're doing a does not equals test, this will get you the p-value on a does not equals test. This is the greater than test, and this is the less than test. So you really have your does not equals test where you enter in the t-score. Good to see you, Andrew. You've got your right tail test, which is greater than. You've got your less than tail. I rarely use that one. You can if you want. And then you've got your confidence interval. So that's how I use these. Does not equals test, greater than test, less than test, and confidence interval right here. So, Connor, you're awesome. And Connor's been helping out. A lot of good. I got an email from someone today saying it was a huge help. So Connor, thank you so much. He's helping one-on-one with students. I really appreciate it. StatLab is still open. So let's go right here. And it's going to probably be crazy with... So we've got the Zoom links I sent out. Sydney, you should have them. So the Zoom links are where Connor is helping out. So if you see the Zoom links, that is Connor helping out right there. We got him a Zoom Pro account. And that's awesome. 286.7 plus or minus. All I did was solve for the margin of error right here. Once again, I just solved that last part of the equation. So that's 1.332. No dot right there. And then we got the hot dog problem next, I believe. So then let's hop back over to here. Let's enter in our numbers. So there's our margin of error. And we can almost do it in our head. If I do it in my head, I'm going to make a mistake. If I type it in, I'll probably make a mistake too. So 288 right here, that rounds to one decimal. And then we go 286.7 minus that. So 285.4. 285.4. That should be right there. Now here's where it gets a little bit tricky right here. Thank you, Connor, right there, putting it in chat. So what is the problem with this experiment? With this experiment right here, we're only choosing the top golfers, so that's not good. We want a random sample that does not pass randomization. And then also we're doing the mean of them. These are all means of top golfers. So we took the average driving distance of these golfers. So no, the means driving distance give a more accurate. So this is not, when you do, and this is the hard thing, I'll explain. We'll check all our answers. Oh, wait. So the data, looks like I got a typo up here because everything else is right. So the sample is not random because only top golfers were chosen. That's correct. We'll just double check. Of course, that's correct. And then this one should be correct also. Oh, wait. Oh, is this a concern? Oh, you got to read the questions carefully, everyone. It's so easy. The reason is, once again, I thought it said, is this interval accurate? Sorry about that. Read your questions slowly. It's in the video now. That's my one mistake of the day. Oh, it's so good this morning. No mistakes this morning. But it's asking, is this a concern when interpreting the interval? And what's going on right here is we're taking only the top golfers. I also did this question a few days ago and I got it right. It's just read your questions slowly and carefully. When you're doing confidence intervals, you want to take single observations from distributions from random golfers. But what we're doing right now is we're taking non-random golfers, and then we're taking a whole bunch of observations from them and taking the average for golfers. So this is a concern. Yes, this is a concern. I thought it says this interval accurate, and this interval would not be accurate, so the interval is not accurate. No, and this is a major concern because this isn't an interval for individual observations and the mean of those observations. It's actually what we would kind of call in statistics Y bar bar, because that means the mean of the mean. So we're taking the mean of the mean for golfers. So Connor, are you in Charlie Quick's class? Have you talked about Y bar bar? Because that's you can get the mean of stuff. So that's the mean of the mean right there. But also it's non-random too. So this is a problem in this problem. Basically, we're not using single observations. We're using the average for golfers. And then, yeah. Oh, you didn't take the 320 yet, or 310? That's 310 right there. So it's a Y bar bar problem. So there's actually less variation than the mean. So this interval is going to be way too tight because there's less variation. You took 370. Ah, yeah, 370S is awesome. So are you taking that right now? I think we got the Nutrition Hot Dog Lab one. I was like, I thought I did my interval right, and I did do my interval right. I just clicked a multiple choice wrong. So awesome. Glad to hear. 370 is like one of my favorite classes. There's so many. So 10% is okay because we assume it's all golfers. Yeah, it's a weird question and it doesn't go into too much detail, but we definitely haven't oversampled all golfers. So 10% would mean we sample less than 10% of all golfers, and they sampled 202. So 202 is less than 10% of all golfers. But they only took the top golfers, so it's not random. And then also, this is a concern. So yes, it is a concern. The interval does have problems, yes, because we're doing it for the mean. We're not doing it for single observations. And that's what we're supposed to be collecting. We're supposed to literally be collecting random golfers driving the ball and not the top golfers, which is not random. And then we're not supposed to be doing the mean of those top golfers. So this is an improperly interpreted interval. So it's good to have a problem that kind of shows you here's problems that can occur. This problem right here, let's jump into it. Great job right there, Katie. I make the mistakes so you guys don't have to. That's my motto. Let's hop right here and start working this problem right here. we need to identify all the notation. You're welcome. Sorry about that mistake there. It's just like, you click it tells you make a mistake. Everyone's had that. They're like, no. So we have all of our notation marked right here. So I need someone in the chat to help me out. You're welcome, Tracy. I need people in the chat to help me out and tell me what are going to be some of these notations right here. Anyone know any of these notations? It's not open again. People have different due dates in different classes. And so this one's not open right now for our class. But we have a lot of quizzes open. I try to space ours out as much as possible. And I've done it over experience of what works. So it's like we don't have all, because sometimes people get go faster or slower, and people have classes on different dates, so different classes have different due dates. They might, Katie and others might have this due tonight. N equals 40, cool, we got that right here. Boom, N equals 40, that's sample size. I'll go ahead and do the mean. Oh, nice job, Y bar, nice job, you got the notation. And then we've got the standard deviation right here, and this is gonna help us find the t-score right here, and then we know df equals 39. So as soon as I find what df, good to see you, Adam. So as soon as I find what the degrees of freedom are, I go right to my applet. So I'm going to go right here to the applet and punch in 39 degrees of freedom. And then I'm going to put this interval right here, and I'm going to go and build a 95% confidence interval. So I have now just found the t-score for my interval. There you go. Ours was due at the start of the week. So we have right here the t-score for the interval. So 2.023. We're going to work the same formula we just worked a moment ago. So 2.023, don't forget it, don't type it down wrong. Y bar plus or minus t star, because we get to pick it, with n minus 1 degrees of freedom, s over square root of n. So we go right here, we put in y bar, 315, then we put in plus or minus the t with n minus 1 degrees of freedom, there we go, and then we put in the standard deviation, 35, then we put in the square root of n, 40. As long as we do our math right, we should be good. That's always what we hope. And so let's go right here and start doing the math. 40 square root. There's that. 35 should be a little less than 6. Yeah, good. We times that by 2.023. We're going to do a double check, make sure we got the right number. 2.023. Of course, there it is. And we're going to go back to here. And we're going to take the number we just got. 11. And that's going to round to 11.2, which we should be good on all the rounding of that. So 11.2, well, so 315 plus or minus 11.2. We'll punch it in as we do this right here. So what is y bar bar? That is the mean of the mean. So if you have a whole bunch of means you collect and you take the mean of the mean, because y bar is a mean, and then y bar bar is the mean for those means. So if I were to see on average like how many push-ups people could do, and I like take 10 samples from each individual, and then so I have like 5 people and they each do 10 push-ups, and I see like, or they do it 10 times, like they do 10 different sessions seeing how many push-ups they can do. Then I take the mean of those. So would that be for it'd be if you had 5 people trying 10 times to see how many push-ups they could do, and you would get a mean for each person. Like for you, you were able to do this amount of mean push-ups. Like in the 10 trials, Connor did this amount of push-ups, and then we would divide that, all the means we got from the 5 people by 5, and we would have y bar bar. So that is the mean for the mean amount of push-ups people can do. So it's the mean of the mean, y bar bar. The sample means mean, says y bar bar. Does that make sense right there? Yeah. So if you were to collect sample means, like everyone has their own sample mean, and then take the mean of the sample means, you get y bar bar. And that's actually what they're doing. It would be an estimate of the true sample mean, because what we're seeing is here, it'll be more accurate, but the problem is now you're saying the individual's means. So if my degrees of freedom is higher, t would be different, right? Yep. If your degrees of freedom are higher, t will be different. So you will go into here, and what are your degrees of freedom? Are they like 59, or what are your degrees of freedom? Tinin, am I saying that correctly? You'll put your degrees of freedom into there, and it's 1 minus your sample size. So 1 minus your sample size will be your degrees of freedom. You already have it? Awesome. Glad to hear. Good job. So we just put it into here. We've got our numbers. We go back to our problem. Let's take it over. Let's do it. So we have 315. We're going to copy this number, 315 plus this number. And I think it rounds to 1 decimal, so 326.2. And then we go back and we do 315 minus it, and we get 303.8. And what assumptions do you have to make? Okay, so a little tricky right here. Let's make sure we got this. So we assume that the hot dog weights are random and the distribution is not biased. Pretty good right there. We need to assume that they're normal though, and independent and random basically mean the same thing. So we need to assume that these hot dog weights are normally distributed right there. Is the randomization satisfied? Kind of, maybe, who knows? I always hate those questions. Is the 10% condition satisfied? Definitely, because 40 hot dogs is way less than. So is it satisfied? Yes. It is less than. Don't mix it up. Is the nearly normal condition satisfied? We don't really know, but 40 is pretty large enough for us to go ahead. Explain clearly what the interval means. I am 95% confident that the true mean sodium content in these hot dogs is contained in the interval 33.8 to 32.2. So remember, and I've done this a few times now, that whenever we interpret our interval, we want to say, this is what we need to practice, I am blank percent confident that the true blank, this is the long part, is contained in the interval blank to blank. So I am 95% confident the true mean sodium content of these particular brand of hot dogs is contained in the interval, and then it was whatever my interval was. So there's 3 parts to this. Let's make it clear. The first part is just your confidence level. Part number 1 is confidence level. Part number 2 is going to be what you're talking about. That's the long part, though. I am 95% confident that the true mean sodium content of these hot dogs is contained in the interval, and then you just give the interval. So part number 3 is where you just give the interval. So we have to find one that follows this format right here. Let's take a look at it. And the one that follows the format is, we are 95% confident the true mean sodium content is contained in the interval blank to blank. We got that 100. Of course we did. And so there was another question in here. What was the other question? Monitor aspects, many aspects of elementary and secondary students. Okay, let's do that one right here. And then we can do some more chapter 16. Many aspects, a thing checks out many aspects. Where is it? Where is that problem? There's 1,000 chips. I see something in the chat. The jury one, you got it. We'll do the jury one next here. Did I miss it? Is it chapter, the one about they monitor many aspects? I don't know if I missed it. And then we'll do the jury one next. I don't see it. You'll have to maybe tell me more about the question. I don't see it. Here, we'll do the jury one. It might be in the homework. Tell me if it's in the homework or where I missed it. It might be in the homework. It sounds familiar. I know I've done it before, I think. So let's do the jury one from chapter 16. I believe it's on the quiz right here. My phone's in the way. And here we go right here with chapter 16. Let's bring the chat back up, see how everyone's doing. So in organization monitor, okay, cool. We will do that one next. You guys even know better than me now. Can we do the radioactive one, chapter 15? Yeah. Let's do that right here. We're back on chapter 16 for a moment. So let's do the jury problem right here. Is this the one right here? Is this the one, Tracy, right here? I think it is. Is this one right here? Nonprofit? Yeah, we'll go back to chapter 15 right after this. Is this the one you want right here, Tracy, for, you said the jury one, or is it chapter 15 for jury? We'll see here. It's chapter 15 quiz? Okay, I need to go back. Chapter 15 quiz. So let's hop back to chapter 15 quiz. There we go. Okay, chapter 15 quiz. Let me go back to that. 2 seconds right here. Chapter 15 quiz. And philanthropic. Oh, wait. I didn't preview the questions. 2 seconds. Gotta hit the preview the questions, or else I can't. Or replace questions, actually. Or else I don't see every version of it. Okay, so now we should get the jury question. We'll do the jury one. Was this right here? No, that's writing nulls and alternatives. Twins. Birth disorders. don't see the jury one. Wait, is this it? No, that's the airline luggage. Am I going crazy? Oh wait, I think I saw radioactive fallout. Did not see that one in the chat. I think we found one. It's the criminal jury. Yeah, Sydney said radioactive. So put the very start of the question in there. You just passed the many aspects. Okay, cool. We'll do that one next, Adam. The many aspects. Here, we'll do this one. Then we'll do the next one. We'll do the many aspects one. Great job. And thank you for everyone for being here. It's only got 3 choices. Okay, cool. We will. Did I already do that one? My brain is. Oh wait, didn't I? I'm having like deja vu. I'm having high deja vu right now. Let's hop in right here and do this right here. Oh yeah, thank you. No, thank you so much, Adam. Like that's, I want people to point out and mention like, Brian, you passed it. I'm so blind. And as Kyle would joke, because I'm always talking about the bright lights that I'm under, they melt my mind. He starts laughing every time I mention bright lights. So let me zoom out, and I'm not going to select that one yet. So when you do a problem like this, and then we'll find the one Tracy's working on. So when you do a problem like this, we need to do our 4 steps to do statistical testing. See, yeah, bright light. And so we need to identify all of our notation and then write this out right here. You're under bright lights also? So we go right here. We start highlighting all the numbers we see. Now, there could be things that are not numbers that we need to note. And we'll find those maybe here in a moment. Oh, right here. Is there evidence that it's unusually high? So that's going to be important to us in a moment. So we have right here that this is going to be the sample size. Oh, blind. Oh, yeah, you are my blind buddy right there. So we are both. We could have a contest to see who's more blind. They would only expect, cancer experts estimate that one would expect only about 28 cancer deaths in a group this size. Assume the sample is typical group of people. So that's kind of saying it's random, like they randomly got these people. But this right here is going to lead into P naught. I'm going to put a star on it. It's like P naught star, because it's giving us information about P naught. It's not actually P naught, because P naught needs to be a proportion between certain numbers. So if we were to go and solve this right here, 28 out of 220, because that's what they would expect, it's 0.127. So that is what P naught's going to be equal to, because this is what they would expect. This is the proportion they expected right there. So we go back to our question, and we can see they're already using this right here. You can see it's the same number we just found. Now what we're going to do is we're going to solve this step by step. This is important right here that we can do it on our own and know the steps without my Pearson. Step number 1 is to write your null and alternative hypothesis. So when we write our null and alternative, very start of this video we started this, we're going to write the null states and the alternative states. Now if we can write the null, we can write the alternative, most likely. Now we're testing to see if the proportion of, people who died from cancer, we're going to see if it is equal to what we expected. So that's P for proportion, equals is always there with the null, and we're going to test the value we put for P naught. Then we want to see if this proportion with the alternative is unusually high. That's why I highlighted unusually high, because this is going to give us information about the alternative right here. So now we go to the next part. Part number 2 is to do your statistical test. We write right here P hat minus, P naught, P hat minus P naught Q naught over N square root equals Z. So this is going to solve for our test statistic right here. So crack up in the chat right there. We go right here, we delete these off now, and we put the values in. P naught, we're just going to abbreviate for the moment, but don't abbreviate when you put in your calculator. That's where people make mistakes. So P hat, we got to find that too. P hat is going to be 45 divided by 220. P hat is 0.20454545. So 0.2045 repeating. And then we have right here P naught. And then we go P naught on the bottom. Then we times that by Q naught. So let's go find Q naught right here. 1 minus P naught is Q naught, 8727 repeating. So 0.8727 repeating over the sample size of 220. So now this will help us find Z right here. And let's give it a shot. So there's Q naught, there's P naught, divide by N, square root, We get that right there, so we copy that. Then we do 0.2445454545 minus, and then it goes 0.12727272727. So that's that. We divide by the standard error. Then we get the following z-score. So that's 3.44 rounded to 2 decimal places, 3.44. This can be done in the calculator under one prop z-test. I've got some videos on that. So that's one prop z-test can be done on the TI calculator pretty quickly, and it'll solve even for the p-value next. So we can basically get the p-value here. It's going to be very, very tiny. We need to make sure we get it correct, though. So, whoops, part number 3. Part number 3 right here is going to be drawing the normal distribution. And then we want to go above. Reason for above is this right here. So we want to go out 3.5 standard deviations on the curve. And then we would plot the area underneath. Whoops. Plot the area. It's p hat minus p naught. Oh, did I do it wrong? That is the p hat. I have it right, Sydney, right? Is it? Oh, you're asking the question. Is it? Yep. You are correct, Sydney. It is p hat minus p naught, which is the observed minus the expected. So p hat is what we observed in a sample, and p naught is what we expect according to the null. So good job, Sydney. Amazing work. Million points right there. Thank you for the clarification. I might have misspoke. I do that every once in a while. But it is p hat minus p naught. And so this is our p-value right there. You can tell it's very, 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 very small. And we can find this by going over to the David M. Lane applet. You can actually do it right here too if you want, but this one doesn't always carry enough decimals. So I do suggest using David M. Lane. So let's bring David M. Lane on the screen, just to make sure we have all the decimals we need with this. So here's David M. Lane. Let's bring it over here. And then let's do the above 3.44. And there we go, 0.0003. 0003. So let's go ahead and get our answers in here, see if we got it. So now we've got that we are doing greater than. We found a z-statistic of 3.44. We found a p-value of 0.0003, very, very small. And then is the death rate unusually high? The p-value is low, definitely, to conclude that the death rate is unusually high. Let's double check our wording right here. The p-value is too high. Or wait, the p-value is high enough to conclude that the death rate is unusually high. Does this prove that exposure to radiation increases the risk of cancer? We can't say. Whether the death rate by cancer is unusually high or not, the cause cannot be determined. This is because this is not an experiment. We didn't randomize who was in the study. We don't have an element of control right here. So we can't do that right here. And I'm missing a spot. Oh, are the assumptions met? So that's the thing, is it's not randomized, it's not really an experiment, but we're going to say it's met, which I guess I have my qualms with that because there's small issues with it. So, oh my gosh, what is going on with me today here? So the p-value is high enough to conclude that the death rate is unusually high. The p-value is high enough to conclude that the p-value is too high. Nope. Did I get my p-value wrong? Let me look at my z-score again. Z-score of 2 decimals for that, 4 decimals for this. The p-value, and did I do greater than? The proportion is greater than. Let's just do our check. My brain is roasted today. This should be right here. Don't tell me I was off by 1 decimal on something. Yep, these are all right. Easiest thing to check are those. Let's check this by putting in a wrong number. That was right. So let's check. It's the p-value, is it? Is the observed death rate unusually high? The p-value is high enough to include... Yeah, that should be right there also. Oh, really? Oh my gosh. What is going on, guys? Oh my gosh, what is going on? Wow. When the p-value is low, reject the null. I've said that a million times. Wow, that's embarrassing. That's embarrassing. It's the multiple choice. So when the p-value is low, reject the null. The p-value is low enough. I was thinking that the proportion was high. Sorry. Once again, I'm not usually... I swear it's bright lights. Like... If you guys can't tell, this like actually heats up the room pretty much. So I'm like sitting underneath heat. Oh, I'm not perfect, Adam. I've made 2 mistakes today, so I'm not happy about that. I only get the 1 mistake a day, so I'm 1 mistake more than what I get. Because everyone knows when the p-value is low, reject the null. And I just have to look at the p-value and say, well, the p-value is low, I reject the null. And so that's literally step number 4 right here. The p-value is low. I don't know why I was saying it was high, because I can't read today. And we reject the null. The p-value here is low, so we reject the null. I wish I'd only made... No, I appreciate it. I appreciate people are in good spirits. So I can delete those parts of the video, but so I could just bring the bright light over this way and just do like this. This is literally, if you can see, this is right off screen right here. Like, look at how little I need to bring it in to have this light, like right here. It's literally at the edge of the screen illuminating. But that's not the only bright light. There's a bright light over here on me, right over here. This one's further away, but now I'm just walking into the sun right there. So this, you can't even see this one, but yeah, so I've got two bright lights on me because I'm illuminating the green screen behind me to get this effect. So it definitely very hot lights. that's what I'm blaming it on. Can Z be negative? Yep, Z can be negative if your P hat was below P naught. So how hot is the room right now? I literally turn on the air conditioner pretty low after all this. My energy bills, hopefully it's not crazy, but you know, I'm running a bunch of electronics, and so I'm running like a supercomputer, running cameras, running bright lights in a tiny little room. The national vital statistics, you bet. So it's not, this room was not optimized for this. So if it's really crazy, I'll tell them. I'll be like, so my energy bill was $400 this month. That was really expensive. So my energy bill was. Is this, someone wanted to do this one? I see, look, can we do the national vital statistics? We're going to ace this one. We got this one. We're going to ace it. Here we go. We got this. Let's do this. You ready? This is our redemption arc right here. You ready? We got this. So let's do this. It's trending for the next... Is that your suggestion, Andrew? I just plug into my neighbor's power grid. Have a good night, Connor. So let's do that right here. This bright light right here on me. So we'll do the jury one right after this. Read to me the start of the jury question. Like, what does it start out with for the jury question? Like, what is the first? Like, in this one is a National Vital Statistics Report, and it's quiz 15. If it's quiz 15, give me the very start of this one. It's their problem. It's not mine. So when we do this problem right here, let's identify the notation in it. Remember, when the p-value is low, reject the null. When the p-value is high, just let it fly. Don't reject that null. So we're identifying all the notation right here. And we see here that this is going to be P naught right here. And we go right here. And this is going to be X. And this is going to be N. And from X over N, we can get P hat. So let's go ahead and solve P hat right here. So, and then Tracy will put the other one. We'll do Tracy's problem next. In the criminal, I think that's chapter 16, is it not? Oh, is it true false? Here, we'll do that one next. I guess it might be this chapter. So that is P hat right here, 0.01550. There you go. Yes, check those points. I think the points are working up right now. So 0.01550 is P hat because that is the number of successes over the number of trials. And then what do we do next? We need to write our null and alternative. Now, this one wants to test. So test to see if it is the same. So we're seeing if it's the same. So that's big stuff right there. I think Streamlabs should be working. It should be. So I'm waiting for it to appear on the screen. Someone checked it earlier and it didn't do anything, so I was a little afraid. But, so, yeah, we'll do that one next, Tracy. We will find that. I think Andrew typed right. Is Streamlabs not working? I changed some settings on the channel yesterday. So you got it. Great job, Sydney. P equals P, and we're asking if it's the same, so it's not equals. I hope I know. I'll have to look into that to see if Streamlabs is having issues. So it's P equal to P naught equal to P naught. Now we're going to go right here. I'm going to write the numbers in the equation. It's P hat minus P naught over P naught Q naught over N square root. Yes, Streamlabs should be working right now. We're on a public stream. We've been up for a little bit, and I don't know why Streamlabs wouldn't show you your points, and I don't like that. I've been wanting to have it work consistently. So I need to do P hat right here minus P naught. My cool video for Julio yesterday got us a copyright claim, not a copyright strike, copyright claim, which we're all right. It's just they could then monetize the video, but I removed the parts out. I was so bummed. I was like, why? I just showed. I put audio over it. I know, Streamlabs is having such an off day. That's so weird. And so now we go into here. We go P naught times. QAnon, thank you everyone who came to the Julio stream yesterday. That was tons of fun. He's such a great interview. Like, I just love his excitement for statistics and everything. It gets me excited for statistics. There is the z-score. Oh, no, you would not accept the null. Fail to reject the null hypothesis, reject the null hypothesis. Yeah, so you will never accept the null. Never accept the null. So that should be a big clue on that one right there. Do not accept the null. We will either... Is it when someone is pronounced like not guilty, is it? If someone is pronounced not guilty, then that is when we would fail to reject the null hypothesis. If it's talking about like they're not guilty, that's the same as failing to reject the null hypothesis. Because we don't accept the null, we fail to reject the null. So if someone is said to be, yep, so it would be fail to reject. So in the criminal case, you wouldn't say, I accept that they're not guilty. You would say, we did not have evidence to find that they were guilty. We will continue to believe that they are not guilty. So you're not saying, I have accepted they are not guilty. You're saying, we don't have evidence to say they're guilty. So you don't know that they're innocent or not guilty. You're just saying, we don't have reason to believe they're guilty. It's interesting how we do stuff in statistics. If we had evidence, we'd reject the null and say we have evidence they're guilty. But if we don't, we would say, I don't have enough evidence to reject the null, and I can't conclude they are guilty. This is the z-score right here. Great job, Tracy, right there. Thank you. I do remember that question now that you mentioned it. So you would retain the null. Sometimes it's called retain the null too. So there's so many different ways you can hear it written. You're welcome, Tracy. And then we go right here. And we draw out a curve. So we're asking if it's different. Does anyone have a guess? Okay, this is my redemption arc right here. I'm going to guess the p-value on this. I'm going to guess the p-value. We see now I'll guess it, but then I'm not going to let it show it's wrong because I want everyone to see me getting wrong answers. So the z-score here is negative 7.3, which is near a number I know. But why is Brian going to do this right here? Why is Brian going to do this? Can someone explain to me in the chat why I'm reflecting it on the other side? So why do I have negative 0.73? And then why am I reflecting over here positive? Why am I doing that? Why did I reflect it on the other side to get the p-value? Correct. And why do I want to find outside? You're very correct, Sydney. Excellent work. Why do I want to find outside? Why am I doing outside? Why am I doing the outside area on this test? Why is this the outside area on the test? Why is it not like greater than or less than? I think people in the chat might know it. This one right here. Correct. Nice job, Sydney. Excellent work. Million points, Tracy and Sydney and everyone else talking in the chat. So you want to find the not equals to, and that's going to be the outside right there. Now, you can probably tell just looking at this, do you think I will reject or not reject? Is the p-value high or low? Is it too high or too low? I don't like the way they word it. You just can look at it every time and say that p-value is very blank. I would blank this with the null. So that p-value looks very high or very low. And when the p-value is low, reject the null. When the p-value is high, just let it fly. Just look at it graphically. Did I shade a lot of the curve or a little bit of the curve? So if you remember from the previous problem where we had a very low p-value, the very low p-value looked like this. This is the p-value right here being shaded. So in the last one, I shaded it there and it's very low. And then the p-value here, just think of that as like a block of gold or something. Did I shade most of that? Like this thing right here, did I shade a lot or a little of it? Did I shade a lot or a little of that curve? Now, it's hard to tell sometimes how much I shaded, but does that look like a lot or a little? So would the p-value be high or low? If it's a lot, it's high. If it's only a little, it could be very low. So which one do we think it's going to be? I shaded a lot, so that means I'm going to not reject because the p-value is very high, so I'm not going to reject. The p-value is high, just let the null fly, so I'm going to not reject the null right there. And so we can find out this exact value, but we're going to go ahead and put in, we fail to reject. Bingo, fail to reject is another way of saying it. Sydney, 5 million points, mega points right there. I like that you said that. It's a more classical way. I like not reject. The reason I like not reject sometimes is because when I say we reject, we have evidence. We do not reject, we do not have evidence. But you could say we fail to find evidence. So I guess that's another way. You could say I reject, I have evidence for the alternative. I reject the null, I have evidence for the alternative. I fail to reject the null, I fail to find evidence for the alternative. So that's like you can use I failed to find evidence for the alternative like that. Just make sure you use the same wording. It can help out with understanding where these problems are at. So great job, Sydney. Excellent work. Do we meet the conditions? Random, 10%. Success, failure. We do meet them. Click the wrong button. It's a good way to lose points too. We're seeing if it has changed, so we're good there. We need to go grab our Z statistic. And look, that's where I made a mistake yesterday. I was clicking buttons. And we're going to put it down to 2 decimals. Now here's my redemption arc. The p-value here. It's a tough one. I didn't draw it graphically accurate. It's not going to look like the drawing exactly. But the p-value is probably close to about 22. Oh, to 3 decimals. Cool. I say the p-value is this right here. I'm going there. What is your conclusion? We're using a 0.05 alpha. We failed to reject the null. You know what? This is my redemption right here. I need... Okay, let's see. I got the p-value wrong. I'll take one more shot at that. Okay, let's find out what the right p-value is. So I assume it's the p-value. Let's take a look. We're doing the outside test. We put in that, and we put in this right here. And, oh my gosh, what is going on with my brain today? I just needed to double it. Oh my gosh. If you notice, I was saying about 23%, and I was doing just the one side of it in my head. So I didn't double it, and if I had just doubled it, I would have been very close to the right answer. I was just doing the outside because I was doing it. I just go to the thing, we're doing the outside test. That one we were guessing at. Remember that. We were guessing at that one right here, so that was our guessing on it. And now everything rounds to this. We click OK, and we check it, and it likes it. So once again, I've run out of Red Bull. We're running only on coffee, on morning coffee right here. So this one was just us guessing it right here. So don't worry, it's the does not equals right here. So we have to shade both sides, and here's how to get the p-value right here. So make sure you can take guesses at it if you want. I was using a number I knew in my head, which is 0.673, and let's do the negative of that, and then the 0.673 here. So that's about 50%, and I was going off of that, but I was only going off of the below, and my brain was just going not. So that's where I was estimating about 23% or so. So you can use some numbers you know, like below 1 should be about 16%, very close to, or below -1. So my brain's just not on. There's about 16%. Above 1 is also about 16%. So if you do the above right here, it'll be about 16%. What other questions are there? What other questions are there? That one was just us guessing it. Here, we're going to do, you ready? We're going to do my redemption problems because I've got a few favorite problems that I really, really like. And I think they're towards, I know where they're at. My favorite problems to do in this to guess are going to be about, they're in the middle here, aren't they? Where are you? Questions. Are they in chapter 16? They're the T-score ones. I have gone totally mad. Oh, you know what I think it is chapter 14. Chapter 14 has those ones I love to guess. They're my favorite questions. So chapter 14 quiz. So maybe someone's working chapter 14 right now. Here we go. Let's find this chapter 14 question right here. Here we go. Perfect. Ooh, it gave us tricky ones. Okay, I can get this second one right here. This second one I know I can get correct. We'll see if people have questions in the chat. I'm up for more chapter 14. Yeah, whatever you want me to do in chapter 14, just mention it chapter 14. This one is very hard to guess. That's a super hard one to guess. This one's not bad right here. I've done something like this, 2 decimals. That one's going to be that. And then this one right here is really, really hard. This one right here is going to be like, it's really a tough one. I don't know. That top one I'm not going to be able to guess well. So it's the bottom one I got right. I'd be shocked if it's the top one. But, okay, so the top one, we have to go get the degrees of freedom into the t-applet. And the degrees of freedom in the t-applet is 24, and it wanted a 99% confidence interval. So it's 2.8. 2.8. I put 3.38 and told me it was wrong because it's 4. Yeah, I'll correct that for you, Sydney. No worries. That's just a rounding thing with decimals. Don't worry. As I've shown today, we all make mistakes every once in a while. So I can correct that. Just email me and say, hey, Brian, correct this. Don't worry. I make mistakes. You make mistakes. When it's small and it's obvious that, you know, wrong number was put in, I correct it. Like, I do rounding errors. Now, this one, this is impossible to guess, at least with my knowledge. So can you do the question about the flights leaving on next? Yeah, let's do that. This is, I can't guess this top one. I can guess the bottom one. The bottom one is going to be 2.3263, and that's going to be 2.33 or 2.34, let's say. And then this top one is so impossible to guess. 14. Oh, got the bottom one wrong too. 2.3263. So is it 2.33? Oh, wow. My guessing is off today. Wow. Okay. It's my last guess, and then I'm going to take a look at these. There we go. If you notice, I was saying like very close to right answer, but yep. It's hard to guess some of these, but let's go over and look at this. So this bottom one right here had the following. It had 112 degrees of freedom, 98% confidence. So 112 degrees of freedom, 98% confidence. So there's the answer right there to that one. And then the top one is impossible to guess, or at least with my knowledge of it. I knew it was very large. If you notice, I was guessing very big numbers, so it's 9.93. And knowing how to use this applet, if you're watching this right now, I'm dropping it in the chat. So this is the applet I'm using right here, where you can put in the percent confidence for the interval right here, and then you put in how many degrees of freedom you want. You put in the percent confidence. It shades that portion of the curve, and it gives you the t statistic. You go back to the question, and you go over here. I knew it would be very large. I just could not get it right. And the answer for this one's actually 2.36 more exactly. It just has a margin of error that gives it to you. So can you do the question about the flights leaving next? You bet. I think it's proportion of flights leaving on time. So let's do the flights leaving. Is it this one right here? I think it is. So this one right here has in it notation that we need to grab. So we need to take this notation right here and work on it. So let's take our notation and start working on this problem right here. Oh, you're awesome. Have a great Easter weekend too. Good to see you, Sydney. Appreciate all your hard work. I know everyone's been working super hard on this stuff. And I know it's a lot, like everyone being at home now. And it's like, okay, got to log online, got to do some work. And I really appreciate it. So what do we have right here? We have n, we have y bar. So n is sample size. Y bar is sample mean. And s is standard deviation. So the last thing we need to put into here is degrees of freedom. So degrees of freedom is equal to n minus 1. So we take n minus 1, and we get degrees of freedom are 71. Now, once again, as soon as I know my degrees of freedom, that moment I find my degrees of freedom, I instantaneously go over to the site right here. I put in my degrees of freedom. And for the moment, I'm going to assume they want a 95% confidence interval. Let me check the question. Where are you at, question? It doesn't say yet, but we'll assume. Let's check the conditions right here. So we will assume that all the conditions are met. So let's see here. Assume all the conditions are met. Well, look. Let's see. No, they are random. The 10% condition is not met. Oh, no, they're all met. So we have all the conditions are met. And 99%. I was wrong. I should not have assumed. They want a 99% confidence interval, which means I need to change this to 99. So here is my t-score. So let's go ahead and start writing this down. 2.647. So my t-score is equal to 2.647. So we got that right there. So let's go into this and start writing the equation. Y bar plus or minus t star with n minus 1 degrees of freedom, s over square root of n. And so now we need to identify all the notation we have right here. Y bar is going to be 24.3750 plus or minus the t star, which is 2.647. And then we have the s, which is 2. Oh my gosh, so many things on the screen, so many decimals. And then we do square root of 72. So much math on the screen right now. So much math on the screen. And so let's take 2.69753. Oh, we got to take divide by. So 72 square root, copy that. 2.69. When does the... Oh, that's the degrees of freedom. That's from n minus 1 right there, Huan. Great question. Not for this problem, but for the normal problems in general. Real quick question. Do we have to assume that there are no outliers? Kind of, Daniel. Kind of. That's a really good question. It depends on... What it is this is the large enough n condition. If there are light outliers, you're pretty good. But if you have extreme outliers or major problems, then that will cause problems with normality. So if you only have 10 observations and you have an extreme outlier, that's probably pretty bad and doesn't pass the nearly normal condition. But if you have like 100 observations and there's like a light outlier, maybe another second small one, not that big of a deal. And if you have a specific problem you're working on, I can take a look at it. But if there are extreme outliers, that's a problem. But usually you want to assume that there's not any extreme outliers. So it sounds like a yes right there. Usually you don't want big outliers. So that's probably a yes right there. And we're writing this in right here. So good question, Daniel. So we go right here, and that's what nearly normal basically means, is we want the distribution to be basically normal. And so you don't want extreme skew, extreme outliers. You want it to be sort of an n of 45. That would be a problem. Yeah, you wouldn't want extreme outliers. That's like a medium sample size. So you would not want to have too extreme of outliers. If you have a specific problem you want me to look at, I can. So that's what I always like or dislike, is my Pearson has like static answers. A lot of these concepts are pretty complicated, and they try to boil it down into like a yes, no. And it's really cool in like 320. We have very, not really advanced ways, but more specific ways to look at stuff. So there we go right there. And we've got it. And let's go ahead. You're welcome, Daniel and Huan. So good to see you guys and gals. So we've got this number right here. And let's go back. We assume all the conditions are met. I think I did my math correctly. I kind of like blanked out while doing that. Went into like autopilot. So there's the upper bound of the interval, 25.22. Does it want 2 decimals? Don't click a wrong button. Did that yesterday. Maybe 2 days ago. I don't know. Days are blurring together. So 24.375 minus this right here. 23.53. So I am 99% confident the true proportion of flights that'll be delayed, I think it is contained in the interval. So statistics delayed is contained in the interval here to here. So we can be 99% confident that the interval contains the true monthly percentage of delayed flights. Remember, we already wrote out how to do this earlier. I am blank percent confident that the true blank is contained in the interval blank to blank. I am 99% confident the true proportion of, the true mean of flights that are delayed is contained the true mean proportion of flights that are delayed, because we're collecting on how often are flights delayed. So it's a pretty crazy thing because we're doing the mean percentage. So it's a little tricky right here, but we would kind of look at each day, I believe it is right here, and see what percent of flights are delayed. So this is not a yes-no question. I know I said proportions, I know it's saying percentage right here, but we're seeing like we go to the airport on a certain day and we look at what percent of flights are delayed. So you're not looking at an individual flight right here. You're looking, okay, on this day, only 10% of flights were delayed. Then over here, there's 2 days where like 30, so that's 33% or so of flights were delayed on those 2 days out of this 72-day sample. So all of these are quantitative measures, but it's a percentage being measured, and we should have it. Let me double check. Get so afraid. Yeah, we got this. Of course we got this. This is our redemption arc. We got this. So, and what other questions are there? What other questions are there on any other problems? I might just sneak back to my secret favorite problems over here. Oh, we're going to get this. You ready? We got this. 95, so that's 2. So the maze one, let's do the rat maze one next. The psychology experiment rat maze. It's going to be like that. That's my guess on that one. And then 2.42. 44. Let's try it. 0. No! Oh, that's way off. Darn. Let's see the right answers on these again. So 23.95. 23.95, it's 2.07. So 2.07, we were close on that one, no cigar though. And then 98 with 58 degrees of freedom. So 98 with 53. And that was 2.40. So we were very close on the second one, 2.40. We were, close, but didn't get them. Practice, quiz, and test. You can choose the chapter to practice. Go to the assignments in My Pearson. Click on all assignments. Thank you so much, Tracy. Can we do the startup company? We'll do the maze and then the startup company. Let's do the maze one. I think it's the first one. So the maze or startup. We're going to do whichever one we hit first. Maze or startup. So we've got that one. The maze or the startup. Tell me if I'm in the right section. So The maze or the startup? Here we go. We got the rat question. Cool. Now this one I really like because this one we're going to get to do it on jump right here. 15. Cool. We got you next, Sam, right there. So this one we're going to get to do in jump because it gives us data. So we're going to go ahead and click on this data here and copy it to the clipboard, and we're going to hit Control-C or Command-C on a Mac. Remember, you can stop this video or slow it down, but all I did was go to the following screen. I'm going to copy the data. So once we copy the data right here, we're going to go into jump, and then we're going to open a new worksheet. Now this is where people usually make a mistake, and I'll show you how I did that. I go here to File, and I go to New, and that's why I use the shortcuts, and I use this right here, and the shortcuts over there on the screen for you to see. So we open up a new worksheet. Now make sure you either paste with column names or paste just regular. This one, we need to paste with column names. So if you look here, I have made a mistake right now because time is in the first row. Now don't try to fix this. Don't try to fix it. Just close it out and go right here to File, New, Data, and then go to Edit, Paste with Column Names. So don't try to fix it. Parking garage problem, we can do that when we'll do parking garage, and we'll go to chapter 15 again. So we have right here, this right here. We've got the data in here. Let's look at this. On the right, it's incorrect because it's categorical. That represents categorical, and don't try to fix it. Just restart it. And over here, this is correct. So this is the wrong way. That's the wrong way. This is the right way, pasting with column names. What we can do is we can go to Analyze, and we can go to Distribution, pausing out of here for everybody, and then we're going to double-click the variable name and just put it right there and go to OK. We're going to go to the top and go to Stack just to make it look all nice pretty right there, and here is our distribution. So when we do this right here, we can get the 95% confidence interval really quickly because it's going to give us the 95% confidence interval inside of jump. 95% confidence interval is 45.93, so let's put that right here. 45.93 to 58.47. All I'm doing is taking these 95% confidence interval numbers from right here. So these are the 95% confidence intervals right here. If it were to give you another thing like 99, you can go to confidence and change it. You'll just put in something like 0.99, and that'll give you the other confidence interval, whatever you want. There's the lower for the mean, there's the upper for the mean. So these are the mean, confidence interval for the mean, 99%, because that's 1 minus alpha. Just like this right here is a 95% confidence interval. So it didn't ask for that, so we won't do it. So now it wants us to view the distribution. Now if you notice, none of these distributions look exactly like ours because they're going from 20 to 100 with a bin width of 5, it looks like. How do I know that? Let's take a look. If you look right here, this is 20, 25, 30, 35, 40. So these are bin widths of 5. So we need to make our graphic look like their graphic. That's the goal of this. Let's decrease font size here. And so let's go back in, double click this, just go right here and double click. And now we're going to go from 20, I'm going to hit tab to 100 and hit tab again by increments of 5. The lower bound here is 20, the upper bound is 100. We're going by increments of 5. We click OK, and now we see which graphic looks like ours. If you notice, be right back here real quick. I think I can do this right here. Back on. Hello, microphone. I am back. Spring back on the camera. Ayo! Back. So could you help me? So there we go. And I might have the parking garage. I might have to go here in a moment, but I have the parking garage in another video. So here we are. If you look, we've got this outlier here. And does everyone see how this is stacked right here with the 2 right there? So we're going to go here and go to D. And you see this kind of has the ridge at the top with the 2 and the outlier. Now we need to look at a normal probability plot. So for this one right here, we've got an outlier at the top side of it. So you've got this outlier up here, and so this is the outlier. It was a very, very high time, and we can actually do this inside of Jump also by going here, and it looks a little bit differently the way Jump plots it, but you can kind of see the same thing going on, that you've got an outlier up here, and actually it's way over there. There's the outlier. That's that one. So that's that, and then here's the outlier up there. It must go up and to the right, so we have that it has to be this one. This is like a perfect one, and this one is going to be a little bit crazier. This one might be the one you're talking about. So we have here an outlier right here. So, oh, you guys are awesome. And Connor, I might hand it off to you, so you might get to help out here. And I've got the parking garage one in the video. So the randomization condition is met. The normal probability plot is not straight. It's roughly straight. So it's roughly straight with one outlier. Without the outlier, the condition seems to be met. It's not bimodal. It is unimodal. We need it to be unimodal. It might look at like it has a second little mode, but it's really just one mode. For the last part right here, we're going to eliminate that outlier. So let's go ahead and eliminate the outlier right here. We're going to click on this, and then we're going to go to rows, and then we're going to go to hide and exclude. We're going to go right here to the very top, go to redo, and redo analysis. So if you look, we have just removed that 1 point. It's out of the picture now. And so the outlier is gone. We have 20 instead of 21. And so our new interval is 45.39. So 45.39. And then the upper of our new interval is 54.77. If you look at these intervals, we're trying to do like a 1 minute maze. So these intervals would not actually contain the 1 minute right here. So we go down, and does this interval meet the 1 minute? Does the maze meet the requirement that it takes at least 1 minute? The maze does not meet the requirement. Both intervals are entirely below. Let's hope I didn't do this one too quickly. Oh, the QQ plot in R wasn't right for it? Really? Connor, was it not? I need to talk to my Pearson about this one because their plots look a little bit weird. So the easiest way to know this one is that QQ plots have to go, aw, Zach, you're awesome. Thank you, Zach. Look at that. We got faith. Zach, you brought back the faith in us. Now we're doing awesome on this. Now we're doing awesome. I think, let's see here. Could you help me with the parking garage one? Let's do the parking garage one. You got it. Now there's sirens outside. You guys can probably get it right here. It's like hoping to lure them downtown. They do the following. Yes. So for this one right here, for Chapter 15 quiz, there's one that's in a criminal jury trial. So if they declare them not guilty, so here, we'll do that one real quick right here. When they declare someone not guilty, the null is going to be you are either guilty or not guilty. So you bet, you guys know where I'm at. So when they declare someone not guilty, what are they doing in a criminal trial? When they declare someone not guilty, what are they doing in a criminal trial? Any ideas on what they're doing in a criminal trial when they declare someone not guilty? Maybe we'll do this. I don't know if I've done the startup one yet. I think I have enough time to do the startup one. What would they be doing in a criminal trial? Oh, no. Remember, there's only two things. There's only two things we do. We either do this or do this. What are our only two options with the null? We either do this or do this. What are the only two things we do with the null? We either reject or we never say the bad A word. We either reject or we do this. We either reject or we do this. Fail to reject. We either reject or fail to reject. So if they're going to say someone's not guilty, what are they doing to the null? Are they rejecting that they're not guilty, or are they failing to reject? No worries, Lindsay. Million points right there, Lindsay. Don't worry. You'll remember it now. You'll be like, oh no, I shocked Brian. You'll remember. You'll be like, okay, we either reject the null or fail to reject the null. Only two options right there. So which one would it be right there, Lindsay? If someone's declared not guilty, would they be rejecting or failing to reject? You got it, Lindsay. Great work right there. You earned it. You got that million points. Great work. It's just the practice that you're like, okay, we can only reject or fail to reject the null. When the p-value is high, reject the null. When the p-value is low, oh my gosh. When the p-value is low, reject the null. When the p-value is high, just let it fly. I made that up. It's these bright lights. It's just melting my brain. Bright lights on all sides of me. When the p-value is low, reject the null. When the p-value is high, just let it fly. High, let it fly. When the p-value is low, reject the null. Low, null, high, fly. It's the rhyme. We got to know our rhymes. Okay. Oh, too much. We were doing a stream earlier today, so I think my brain got burned on 474. So let's see right here. You're welcome, Lindsay. Excellent work. We'll get it right. So we've got here that they're trying to lure people. I'm going to maybe just do a few of these quickly right here before my brain just melts. So once again, what do we do in these questions? We take our notation down. So I'm probably going to mark the notation for this one, and I want you guys to solve it. It is in other videos, though. I have worked this problem a few times, but let's see if you guys can solve it. I want you guys to think about this right here. If you're working this problem, don't erase it. I want you to go in here, and I want you to know what the notation is. So I want you to be like, okay, what is this notation? So we've got this. We've got how many things they collected, the standard deviation, and we have the mean for that group. So we have a mean, a standard deviation, and a sample size. And then from this, we can also get n minus 1, which is the degrees of freedom. So we can get n minus 1 equals degrees of freedom. So we can find out the degrees of freedom, and we need to plug it into the following formula. So we need to plug this into the following formula right here. So this would be n, and that'll get us the proper t down here. And then we have s, and we have y bar. So y bar is 131. Nice job, Daniel. Is this making sense, Daniel? Did you get past this part right here? Do you know how to get the t statistic? Philanthropic, can you read me the rest of it? The philanthropic, I'm trying to think if we did that one today. Is it 15 or 16? Which chapter is that one? We can do that one next. I'm trying to think if I did the philanthropic today already. What assumptions must be met? The data are random. It's unimodal and symmetric. We do not want them to be at least 10%. No, we want it to be less than 10%. And we want that they be independent of each other. Send free mailing labels and greeting cards, chapter 15. Yeah, let's do that one next. We'll do some finishing ones. 99% confidence interval. So I need to go over here. The sample size was 43 with 99% confidence. So we're doing, there we go. Sample size was what again? 43. So we go here and we go 42 with 99% confidence. That's going to be my t statistic. The wording on the next couple questions is difficult. Let's check it out. So we have right here, explain your interval. I am 95% confidence. Let's see here. There's 95% confidence that the mean daily income, not that it will fall inside the interval. There's 99% confidence that the interval contains the mean daily average. I am 99% confident that the interval contains the mean daily average. Explain what 99% confidence means. 99% of samples of size 42 will produce intervals that they will contain the truth. The consultant who advised the city on this project predicted that parking venues would average this. Is he truthful about that? Well, we got to find the interval. Okay, let's do it. We're right there. We got this. So we got to get our number from here. Our number is 2.698. And S was what again? 17 over square root of 43. Plus or minus. No, this is another class doing it right here. So you're welcome, Tracy. Another class doing it right here. They have it due tonight. So we're just working on a few problems here. Different classes have different due dates because instructors get to different points. So some people have it a day earlier, a day later. And I try to space mine out as much as possible. That's always my goal when I give assignments, to like spread them out as far away from each other as possible. So that way you don't, I know we just had 2 due in a row, but it's because they kind of, my Pearson was crashing constantly. Oh, that's so perfect. It's 7. I think it rounds to 7. Yeah, good question, Sam. So this is 7 right here. So as long as it's 7, we're good. So let's see how many decimals it wants. So there you go. There's 99% confidence. So if it's 7, it should be 131 plus 7. So that's 138. And then 131 minus 7. And I think it all rounds. We'll hope the plus or minus is nice to us. So 124. And so let's go right here. Do we think that that's a value? Oh, look. 125 is in the interval, as long as I did everything correctly. So since the 99% confidence interval contains it, the predicted average consultant is plausible. Woo! Got it right. Awesome stuff right there. because 125 was in the confidence interval. Does that make more sense there, Daniel? We're going to hop over to Ashton's question here. But does this one make a little bit more sense? Remember your interpretation here. I am 95% confident the interval contains the mean daily income for this parking garage. And then we would say that 99% of 99% confidence intervals are expected to contain the truth right here. And then since the value is contained in the interval, it is a plausible value. One of the biggest parts for people, because a lot of the question hinges on working this equation over here, you just have to make sure you get the right numbers, put the right numbers in, and then there's some theory questions down below. So we're back on our streak right here. We've been doing excellent now. So you're welcome, Daniel. So glad to have you. We're going to do a chapter 15 question or two, I think. We have enough time for. So let's go and take a look at chapter 15. Chapter 15 quiz. Can we do the start? Yeah, I think people are asking about the startup. Let's see about that. I got the preview going right here. Is it chapter 15? Chapter 15 startup? If you can read to me the start of the question, that's a huge help. I'll find it. Someone wanted philanthropic. I think philanthropic was asked for. Yeah, Ashton asked for that. So, okay, cool. We'll do that one next right here. So, Sam, you got that next. So we have a philanthropic organization is mailing greeting cards, and then we need to copy this question. Let's go ahead and grab it and put our notation on this. So let's grab all this right here and put the notation on it. So we're going to do the notation. You got it. Great questions, everybody. I love the positivity in the chat. Everyone just like sees everyone, talks to everyone. Are the points working again? Andrew checked them earlier, and they were not showing points. I don't know why Streamlabs would not be happy today and not give points. So we've got here this. There we go. So let's do this. This is the sample size right here. This is how many conform to it. And one of the best things is this question is really done well in the TI calculator. Hopes the rate would be higher. So they're hoping the rate would be higher. So now we have to write down our 4 steps for hypothesis testing. Step number 1, write your null and alternative. Step number 2, find the z-score or t-score or chi-squared later on. Step number 3 is going to be to find the p-value, and step number 4 is going to be reject or fail to reject the null. So when we do this problem, we're dealing with some small numbers. That's the least fun part of this problem. So the good part is we can write our null alternative pretty easily because we're testing 5%, and then we can do p hat pretty easily. P hat is going to be equal to 0.05213. And we have here the null and the alternative, and we have to write the true proportion is equal to 0.05 because that is p naught. P naught is what we're saying it's equal to. And then we would say we want to see if it's greater than this. They're trying to see if it's greater than that value. So when we do this part of the equation right here, we do p hat minus p naught over p naught q naught over n square root. This will get us the z-score right here. And I don't know why Streamlabs is not working. I'm going to look into that later tonight. So here we go right here. Let's solve this out. It's going to be a lot of very small numbers on here. So we have p hat, which is this right here, 5713. It's a 3 right there, minus 0.05 over p naught times q naught over n. And that's it, square root of that. So let's go ahead and find the z-score right here. We're going to do the bottom part of the equation first, because we can store it in the calculator. And we divide that by 1, 2, 1, 2, 3. Got it. Then we square root that. That's the bottom of the equation. Now that I think doesn't copy when you do it. So 689202. 689202. So (689202). No way, that's way off. Did I not square root it? Let me double check my numbers. 0.05 times 0.95, p naught times q naught over n, square root, and Could it really be that small? Let me check all my numbers here. 689202. Six, 8, 9, 2, 0, 2. I guess it is a z-score that big. That's pretty crazy right there. 10 point... I feel like something is off. 10.35. 10.35. Let me double check all my numbers right here. Well, thinking about this, you know what I'm going to do? I'm going to go open up R because I want to check my work. And if I'm going to do it correctly, I'm going to make sure it's working correctly. So let's see right here. We're just going to open up a new R script. We're going to put our numbers in here. We know what n is equal to. We know what x is equal to. I think that was x. So we'll do this instead of R right here. There we go. All we're doing is just writing the equations. And then p hat is equal to x over n. And so this is just p hat right here. So that's all we're doing is finding p hat. P naught is equal to 0.05. And then Q naught is equal to 1 minus, move that out of the way here, 1 minus P naught. So if you notice here, I can click Q naught, and that's now equal to that. So then we can write our equation that P hat minus P naught over, and we want the square root of P naught, I need to put in parentheses, P naught times Q naught over n, and there's the square root on that. So that should, there we go. Something's happening wrong with my math. I knew it. What is going on wrong with my math? So I want to check this out because P naught and Q naught, I was like, that did not look right. So there's P naught and Q naught, and n is this. That's 1, 2, yep, 100,000. And then this should be equal to, was it equal to what I had? That is that number right there. There's that. And am I typing this top part in the wrong way? Oh, I was typing a 7. Oh, I know it. Yes. I knew something looked weird. I can't read my own writing. Oh my gosh. Good thing I caught that. I was like, that's a math error right there. That's a 2. I've done this problem a lot, and I'm like, usually it's not that large. So there's a copy error. We're trying to show all the different errors students can make today, because I was like, I would rather just punch in the numbers. This is how I would prefer to solve stuff right here, and I'll show you a really cool trick on this. So that's going to get the z-score right here. So that's the z-score. And then we can do, let's see here, q-norm. So q-norm is going to takes the percentage, so we want p-norm. And we're doing a, I think, and I'll show this off right here, p-norm, we don't want to do that. We want to put in the z right here, good. Yeah, it's going to be a very small p-value. And are we doing the greater than? So we go right here and do 1 minus. Cool. And there's our p-value, it looks like. Is it 0.005? No, the what I was typing in it the wrong way was this value. I put a 0.057, and it's 0.05 for the other one. So this right here is 5%. That is 0.05. What it is was this right here, which should have been 0.052, and I had put a 7 because I can't read my own writing. People joke that my handwriting is so bad, and it's quite true that my handwriting is bad. So that's where the error was, but we caught it before it gave us a bigger error. So I thought I'd written 7 and just looked wrong. But everything else here is correct. I had just done p hat incorrectly. Does that make sense there, Ashton, on how to do this and where my little error was? And so we know the z-score, just doing the mathematics on this, is 3.0905. So let's go back here. 3.0905. Well, we can do this now. We've pretty much got it. We're trying to see if they can increase it. They're trying to make it higher. So that means the true proportion needs to be greater than 0.05. So we're seeing if the true proportion is equal to 0.05. And this value right here, Ashton, that I'm hovering over, that is P naught. Whatever is in this position is P naught. Are the assumptions met? Randomization and independence seem to be met. Success, failure, and 10%. Do you think the donation rate would rise? So we do have evidence. The p-value is very low. So the p-value is very low enough to conclude, and let's show this graphically. We're going to take the p-value we got of 3.09 and go to the David M. Lane, and we want to go above. So we'd go to 3.09, and the p-value is right here of 0.001. And this is what I was doing in R inside of here by getting the p-value here and this is a more decimal accurate p-value of 0.0001. And you see this would round to 0.001, but yeah, so I was just solving this inside of R right here to get the p-value. One cool thing you can do is you could put return on this, and watch this. We can take everything we have right here, write fung, and do this, and go right here. And if someone were to have another question right here for me, so we got all these things, we need to put in n, we'll go x, n, p hat, and p naught. Okay, cool. Let's delete these out right here. And, well, no, p hat will be solved in the equation for us. This is why I love programming. Brian's telling you why he loves programming right here. So this will return the p-value, and let's, I guess we could have it return the z also. So we could do a list. I think we can do this right here. List, let's try that. Okay, cool. Let me try, let's call this, what is this problem called again? Mailer problem. So it's the mailer problem, and let's try it out right here. Mailer problem is going to have, let's say, 5217, and actually it's always 100,000, so you know what? So we don't even need that n. Let's just go right here since it's the mailer problem. So we'll just go inside of here and say n. So all we need is x, and we need p naught. Rerun this right here, and now we get the list. There's the p-value, and there's the other thing. So this is why I love coding right here, because if anyone else does the problem, we can literally go back to here, and so we should have this right. The p-value is low enough to include that the date would be above the previous campaign. We meet all the conditions. We got the right stuff, and we did it, and we got that right there. So I don't think everyone solves out everything in this question. It kind of bums me out. But if we look at another version of this question right here, we've got 529, 5229, and also 5%. But with this code right here, I can literally go and type 5229, and then there's the p-value and everything. So now I know that this one right here, they're trying to see if it's greater than, we meet all the conditions, and the p-value is low enough that we can say that we have it. So we can do another one of it. We can go right here, and then we have, that's, are they trying to see, they're trying to see if it's lower. Oh, I'd have to change the way my code works. So if they're trying to see that it's lower than this, I actually have to change how the code works. I don't want to write my if statements right now. But now the p-value would not be 1 minus. It'd be this right here for the p-value, if it's lower than. So 4820. So 4820, and we run our code, and then there's the z-score of negative 2.6, and then there's the p-value of less than 0.05. So if you notice, this is the power of coding right here. I can just solve all these questions instantaneously because all I'm doing is changing the x values. So this is the x and this is the p naught. It looks like they're constantly testing 0.05, so I could even go here and go p naught and put a default of 0.05. So now this has a default of 0.05, and I don't even need to put 0.05 here. I can just do this, and oh, I could. There's so much more I could write to this, but let me do one more question here. So I think, but you know, I don't know, I like it, because now all you do is you put in your x right there, and it solves the question. Of course, we would have to deal with the less than, greater than, so that solves that right there and gives you the p-value. But that's the power of coding. That's why I love coding. What was the last question we had right here? The startup one I think people want. Let's do the startup question. The startup question. I think they said it was like my first question. This is not the startup. No. Tell me if you guys see the startup question. Just generally believe. Where is that startup? How does the startup question start? Oh, wait, I think this is it, right? A nonprofit, is this it right here? Is this the startup? Is this the one, Sam? You think it's my number 11 or something, I think you said. Oh, wow, you're good, Sam. It is my number 11. Wow, you knew that. Okay, let's take a look right here. So we've got the startup question right here. And let's take a look. Let's grab our notation. That is so much to read. Why can't it just tell us the important numbers? Let's find those important numbers we need to know. We need to make it bigger than that. Oh, I can't see that. Nope, can't make it bigger. We'll go off the screen. Okay, so here we go. A startup company is marketing a new printer. It decides to gamble by running commercials during a championship game. The company has hopes that their name recognition will be worth the high cost of the ads. Okay, so they probably want more name recognition. The goal is that over 36%. Cool. There's our null and there's our alternative. This is what they're going to hypothesize is true, and they want over it, so the over is a keyword for the alternative. The day after the game, a pollster contacts this many people. That's our sample size. And randomly chosen, good, a condition is met, and they find this, that's going to be X right there, and I think we have everything, and here's alpha level right here. So we know everything we need to know for this right here. We know all of our notation. Let's put that notation down here. So this is going to be P naught. This is going to tell us the greater than sign. This right here is X. This right here is N. And this is our alpha level right here, which is the percent of the time we reject the null, the type 1 error probability rate. So from X over N, we need to get P hat. So there's P hat. So remember, we're going to use this here in a moment. Not right now, though. X over N, so 181 divided by 429 equals 42.1911. So there is P hat right there, which is the sample proportion. So in our sample, we saw about 42.1911%. And that does seem high enough that the z-score is probably going to be about 4 or 5, I would guess, just by doing a lot of these problems. I always take guesses because I knew that that last one was way off. I've done it a lot too. But now we need to write our nulls and our alternatives. So null and alternative is first step. Solve for the z-score second step. And then third step, find p-value. And then fourth step, reject or fail to reject. So writing the null and alternative, since we're testing a proportion, we always want to write out. You can write your skeleton if you want. We know that the null goes, we're going to test to see if the true proportion is equal to some hypothesized value, or the true proportion in this instance is greater than some hypothesized value. But what's that value that we're hypothesizing? We've already identified it up top. The value we're going to hypothesize is true and test against is 36%, because we're seeing if there's evidence that more than 36%. So next we have down here, we're going to write our equation of p hat minus p naught over p naught q naught over n square root. And we're going to take and we're going to put those numbers into here. This is what I was putting in R a second ago, made my life a lot easier. That's why I love coding. Coding is awesome. Makes life so easy. I can't solve all these problems in code, or people be like, what are you doing? And I'm like, it's easy. Just code it all out. So we have right here, this is P naught. This is Q naught. This is N. This is, now we have P hat minus it. So we got to write this in real tiny, make sure we can read our own handwriting. It's always a problem. And then we go right here, and we have P hat minus P naught. So P hat minus P naught over P naught Q naught N square root. This equals a z-score. Let's go ahead and find what this z-score is. So we have 0.36 times 0.64 divided by 4029. There we go. We square root. Don't forget to square root. Done that a bunch. Then we're going to subtract the top, and it's going to be right about 3 or 2 point something, I think. So it's very close to my estimate. Should I guess 2.88, I say. Shouldn't talk while I type these things in. No, yeah, 2.67. So I always said it was about 3 or 4. Close-ish, close-ish. So that's where the z is going to go right over here. We're just going to write 2.67. I went to 2 decimals. Now we need to plot this. And we can take a good guess at the p-value on this one. This is our redemption arc, because this one is near a number I know. So we need to plot above this. Now, once again, why are we plotting above 2.67? Why are we going to plot above 2.67? You should know in the chat right now, because of this. Because this points to the right, so we're going to shade to the right of where we landed. This is the z-score right here of 2.67, and so we're going to where the z-score was at and shading above the test statistic. Why above? Because we're testing greater than. Now, if you look, that is very small, and I can tell you from my experience that that is small enough that we will reject the null. So I know right now that that p-value is very small, and we will reject the null. I'll show here in a moment why it's very small. That p-value is going to be about 0.00. Oh, it's going to be smaller than that, right? I'm saying in my head. 0.003, I say. I say 0.003. Very small p-value. Let's find out if we got it right. So we're testing that it's equal to, and we're looking for evidence that it's greater than. Compute the test statistic right here. We solved that out. We took some good guesses at it. 2.67, we copy that in, we put it in here, and we delete down the decimals. Easiest way to make sure we round it right. Make sure you round at the end. And the p-value to 3 decimals, 0.003. Should I do this? Nonprofit question, school dropouts. I think I do. Is that in this one? I think we can. Would you recommend that they do it? Well, they're rejecting the null. The p-value is low, so reject the null. So yes, because the null is rejected, there is sufficient evidence that more than. This is our redemption arc right here. I didn't do this in the applet. I'll do it in a moment. But we got it. Of course we got it. We know how to solve those p-values. So how did I get that p-value? It was near a number I know. This is a z-score, and we want to go above this. So I was very lucky. It's 0.004, but it gave it to me because I was close enough. But I was guesstimating it in my head because I know a number near that. I know this number in my head. So I knew it had to be less than this. So when I saw this z-score right here, I was like, this has to be a little bit less than this. This is 0.005. That's what I was thinking about in my head. And I said, okay, a little bit less. Let's go with 0.003. And it was rounds up to 0.004, but it gave it to me. I guess I could have entered 0.005 and it might have given it to me too. So that's how I guessed that p-value right there to 3 decimal places. So this is how you should do it in the applet. Don't worry, you're not expected to guess these things. I just do it for fun. It's my redemption arc. So it's similar to the question, but I think my calculator's off. Calculator's off. Oh no, let's check it out. Let's check it out. We're on a roll right now. I think we found, wait, no. Is this it right here? The nonprofit, so, is this it right here? Is this the dropout? You're welcome, Sam. Hopefully, glad that helped. Good job, everyone. I think this is right, this. Is this the right one? Oh, this is not the right one. Okay, Lindsay. I was like, it doesn't say nonprofit. Oh, it's not a nonprofit. Oop. Question 9 or so. You guys are so good. Hey, we found it. Okay. There's so much stuff on dropout rates and everything. So let's go here. Let's grab that question. You know what we're going to do. We're going to copy that question. We're going to find that notation. We'll go to this one right here. So we are going to copy and find the notation as quickly as possible. And let's take a look. Here we are. So now we got the question in here, and we can start talking about the notation. So we go here, we get this, we get this, we get this, and the rest just look to be dates and ages, which we don't need. On the school district to adopt the use of the nonprofit program, tutoring whose dropout rate has always been very close to the national average. So they're close to the national average. Is there evidence that the tutoring program has been effective? So if a tutoring program has been effective, the dropout rate would do what? Start thinking about that and answering in the chat. If the tutoring program is effective, the dropout rate should do what? If the tutoring program is effective, we would expect the dropout rate to do what? If the tutoring program is effective, we would expect the dropout rate to do what? And here's the biggest thing. Pause these videos if you're working on these. Work the just less than, Lindsay. Million points right there. Just less than. So we always do less than, greater than, or not equal to. So we would do less than. You might be saying or equal to for the null. So I'll take that for the null. So the null always has the equal sign. And then the only signs for the alternative. So we'll write out our 3 parts right here. The only signs for the alternative that can go in here would be less than, greater than, or not equal to, and the null always has the equal sign. So when we get to the second part of this, we always have to think the null has the equal sign, and we're seeing if we can lower the proportion of people who drop out. Now these 2 spots right here are always going to have the same thing. So whatever I put in these 2 underlined spots, if I put not 0.904 there, this will be 0.904. So we're trying to see if the true proportion has decreased. And so this spot right here on the alternative will either have greater than, not equal to, or less than. Those are the only choices. And we're trying to see if the true proportion has gone down. Try reading it as a sentence. Here, listen as I read these as a sentence. The null hypothesis states that the true proportion of people who are dropping out is equal to 0.094. The alternative states that the true proportion of people dropping out is less than 0.094. So they're trying to show evidence that the true proportion is lower than what it was. They're trying to show evidence that the true proportion has decreased. We'll just write that again. So that is what we got going on right here. And so now for part number 2, We need to identify in our notation, this is x, this is n, this is p naught, and x over n equals p hat. So we're going to put that over here. So we're going to solve p hat real briefly right here for the sample proportion. In our sample, we observed 7.31%. Really tiny over there. Actually wrote decently. So we observed 7.31% in our sample, and then we need to take p hat minus p naught over p naught q naught over n square root. So this is what we need to put right here. There we go. Let's put this in, and we got it. So this will be 0.094, and then we do 1 minus that. So that'd be 0.906, because that's just 100 minus it. We do it over the sample size of this, and then the top of the equation is p hat minus p naught. And this will solve for z right here. Be very careful with all the decimals and everything. It's easy to make a mistake. So we're going to do the bottom part of the equation first. And then we square root. Don't forget your square root. And then 0.731. Got it. 0.094. Got it. And there, wow. Oh, we can guess this one. That's awesome. That rounds to a z-score of -3. As long as I entered in everything correctly, this is a very easy one to guess. So z-score of -3, draw out your curve. On your curve, it's a horrible curve. We can do way better than that. Someone in the chat should know how to guess this one. Because if we have 99.7% inside of here, then what would be in these tails? In one of these tails would be 0.0015. So we can show this again on the applet here in a moment, but we landed right there. So you got it. Nice job in the chats. And so you got it because that's the outside Lindsay. Great answer. Million points, Connor and Lindsay. And so we can figure out the p-value here by just knowing how the empirical works. And this is so low. This p-value is so low. Can't believe I missed that question earlier. This p-value is so low, we're going to reject the null. When the p-value is low, reject the null. When the p-value is high, just let it fly. I don't know how to spell reject. But when the p-value is, I can't divide either. Reject. So reject the null. When the p-value is low, reject null. Oh, you did 0.015. I see it right there. I didn't even notice. Oh, and everyone, yeah. So it should be 0.0015 because it's 0.003. So it'd be 0.0015. Yeah, I didn't even notice the decimal differences right there. Once again, you don't have to solve these in your head because you can go here and copy this. It's probably going to be 0.0016. Let's take a look. I think it's going to be 0.0016. We're going to go below because we're doing a less than alternative. And then I say 0.0016. That's my guess. Let's check it out. Oh, it's 0.0014. I was a little bit off. So it's 0.0014. And I'll tell you why. Because in between -3 and +3 is 99.73. So that's the more exact decimal placement of it, 99.73. We say 68, 95, 99.7, but it's actually 99.73. So that's the decimal differences. Would we have gotten it right with our guesses? So here's the t statistic rounded to z statistic rounded to 2 decimals. P-value, we would have guessed, I think it's not going to get it right for us. We would have guessed this right here. So 4 decimals, I think that's not going to give it to us. Let's put it, here, we'll get it right, then we'll see if we would have gotten it. So it's this, we'll check the applet again. Make sure your applet's confirming your answer. We're going below this. So 0.0014 rounded. So that's the answer right there. Is there evidence that this tutoring program is being effective? Yes, there's evidence that it's lowering the rate of dropout. When you look at your results here on this graphic, what we observed right here on this was very unlikely due to random chance, given the true dropout rate is 0.094 or 9.4%. So we definitely saw what looks to be a significant reduction. So let's see here. The school's observed dropout rate would be highly unusual. I said unusually high. The school's dropout rate would be highly unusual if the national dropout rate was this. Conclude that the tutoring program has been effective. So we think there's evidence it has been effective. And I missed a question, it looks like. So I didn't choose my null alternative. We're trying to see if the true proportion has decreased. So we're trying to see if the true proportion has decreased. We're going to check our answers right here, 100%. And then we go right here and we see if we would have gotten it right with our guesses. So with our guesses, we said this, and we wouldn't have gotten it right. I think there's a plus or minus on the last one. So if we had just used, if we hadn't changed our guess, we would have gotten it. So this answer has on the last one a tiny plus or minus. So it wants you to put in 0.0014. Oh, that's acceptable? Really? Huh. I'm shocked that the range is 0.0012 to 0.0015. So that's the range on that question right there. And here is the answer in the applet right here. I'm just shocked that it accepts 0.0012 to 0.0015. And then if we had guessed 0.0016, which was my guess in my head, I would have been off by the tiniest amount. I would have been off by the last decimal, because that would have accepted it right there. And you could have used the empirical rule to solve it. That's the wrong one. Wrong blank for that. You could have used the empirical rule, and that's actually what we have written on the screen. So if I just taken what I wrote on the screen, I would get it right by guessing it. I think that's got it. We did a good almost 2 hours of work. How's everyone feeling? Do you guys feel like you understand these steps better? Statistical tests are just these 4 steps where we write our null and alternative. We do the statistical test where we check conditions like random, 10%, success, failure. Third step is going to be to find the p-value, and fourth step is going to be reject the null or fail to reject the null. Only 2 choices. We don't say accept. Don't worry. A lot of people have told me that, and I'm like, no, don't say accept. I think that's got it. I think we did a lot of questions today. Timestamp the video. I always appreciate it when people timestamp it. It's a huge help. So if you're watching this video now and you worked a problem, maybe throw a timestamp in the comments, mention what question you did, and that's a huge help to everybody. But I think that's going to do it. Connor, thank you so much for your help. Connor, did you get some people in office hours? Were you helping out? I need to move my camera down a little bit more. So, because I've got so much room up here. I can just everywhere. Reach over to the side now. So it looks like Connor might be helping out. So no one has come in yet. That's all right. You've done some great. I think people came in earlier. Someone told me they came in. My test statistic is 3.18. Does it make sense for my p-value to... yeah, your p-value will be a little bit less. Yours will be like 0.0008. Livia had quite a few earlier. Awesome. Yeah, I heard there was, because I heard people saying it was a huge help. Yeah, people were saying that it was a huge help. So I really appreciate it. That should be your... I said 0.0008, and awesome. Is there a reason why my histogram on jumps does not look like any of my answers? Huan, make sure to go to your histogram and change the bin widths. You'll need to click right here on your histogram and double click it and change it so it looks like the graphic. Does that make sense? Look at the number line, because maybe yours goes from 30 to 100 and goes in increments of 10. So it might look like this. But double click the number line and then go here and go from 20 to whatever it goes. Look at the lower and the upper of it and then see what the increments are. So the bin widths are the literal bins right here, like going from 20 to 25 to 30 to 35. So yes, and throw that in on the comments at the end, Sam. Throw that in. Thank you so much, Sam. Throw that in at the comments at the end. Huan, does that make sense right there? How to do this right here is you'll click this number line and you'll put in the lower number and the upper number, and then you will put in the increments. And so put those in the comments. Thank you so much for all the comments. We should be monetized soon. I'm hoping we get monetized very soon, and we'll keep making content for you guys. Like, comment, subscribe, because it's going to start impacting the channel a lot more, and then we're going to put all the money. Awesome, Huan. So hit a like on the video if you want. It's right below me right here. Just click that thumbs up button if you want. I'm going to end the video here in a moment, maybe reload the video and throw a comment in underneath it. So great job, everybody. Those comments help us, even if you're just like, great class or something like that or whatever, but all the comments help. Thank you guys. And that's the best way you can help the channel, is just to press the like button. You can subscribe if you want. You can always unsubscribe. Like the videos, subscribe, and throw comments under the video, because we're going to take all the money we get from the videos once we start making money, which we hope to happen soon, and then we're just going to put that into tutoring so we can pay people like Connor and Livia. We already do pay them, but we're going to invest more in our tutors and stuff like that. So if this channel becomes a big help for students and we get a bunch of views and we maybe make $1,000 a year, all that money goes into tutoring students. So every like, every comment you give helps us promote the channel. So with that, we will end, and we're going to end with our fun outro video again. So I'll see everybody next time.